This is our monthly NASA at Google talk, and this month we are hosting Jason Crusan, and this is the Pioneering Space Talk, Not Your Great-Great-Grandfather's Manifest Destiny. Jason is the director for the NASA Advanced Exploration Systems Division in the Human Exploration and Operations Missions Directorate. So please welcome me in giving Jason a big hand.
Thanks. So government likes long titles for some ridiculous reason. So, my job is actually kind of split into two things. So I work in our human spaceflight group, and I run one of our divisions, and I'll tell you a little bit about what we do. But we basically do the architecture planning for human spaceflight, and planning is kind of a loose term because we're not setting out a whole sequence of events and all those kind of things, but rather a series of trade studies. And then I run a group of investments on technology and capabilities that do all that. So, and I'll talk about some of those areas there. Encourage questions and those kind of things as we go along. But I want to kind of give you a snapshot of where we're at in NASA's human spaceflight program. People talk about it a lot in the news, and everybody's wondering what's going on with it. I like to start with this picture. It's a very famous photographer took the picture, Neil Armstrong. Buzz Aldrin's on the bottom step coming off the LEM. If you ever run into Buzz, ask him what he was doing on the last step. It's an interesting story in itself. And because he does claim a few first himself. But this is what people think about as human spaceflight. This kind of monolithic goal, go plant flags and footprints, be the first to do X. And actually for quite a long time in human spaceflight planning, that same mantra, especially at NASA, has been the continued mantra, which is let's go to Mars first and plant a flag and be first to do an X. Let's be the first to build a space station for the sake of building a space station and a lot of those kind of things. And I would like to say that this is actually wrong, and Apollo ended for very good reasons, and we should learn from those. At the end of Apollo, we didn't end Apollo because we ran out of hardware. We ran out of a will to keep on going. There was 3 sets of flight hardware at the end of Apollo. They now sit in museums across the country. We didn't run out of stuff to fly, but rather a will to go. And I think that's the cause of that, I suspect, is because of kind of a singular purpose of Apollo and the structure that it was. So what you see here is space station. This is the picture of it as the last shuttle left it during assembly. Space station is a much better model to think about. And folks actually are curious about what stations' actual goals and objectives are as well. Obviously, the political achievement, the technical and political achievement of multiple countries coming together to build something, that was one of the primary purposes. But now it's the utilization of it for technology, advancing technology and understanding fundamental physics in the low Earth environment that help us learn to be able to go further. Understanding biology and science, fundamental science, also in order to send humans off further and longer away from Earth. And one of the other interesting goals of the space station that people don't realize is it's also our first toehold of building a space economy, or at least NASA's contribution to building some of that space economy. Station today, we are utilizing over 50% of its capacity, but non-NASA users. 15% of the global launch business are cargo flights, most of them commercial, going to the space station. There's a whole emergence of deployables off the space station that are now starting to open up multiple businesses. And so this station as kind of an economic growth or at least a government contribution to offset the ability to do economic growth off the planet is really, really important to us, along with learning the things that we want to do in deep space. And at some point, if we are smart about it, we being the global space community, we will show that there's value in low Earth orbit beyond just the government doing it, but rather can you create value in low Earth orbit besides imaging satellites and telecommunications, which are primary industries today. A lot of folks also hang on a talk that was given at NASA Kennedy Space Center by our president. He talked about going to an asteroid by 2025 and going to Mars by the 2030s. And a lot of people take those kind of measurements of dates and then they try to map it back to that Apollo strategy of flags and footprints. And that's a bit of a false thing to go chase. Actually, right before that, he said something that was actually really intriguing that most people don't realize, and it's up there as a quote for you. But my simple summarization is, how do we learn how to send people further and further away from Earth, or longer and longer away from Earth for longer periods of time? So how do you live longer and further from Earth without the reliance of Earth? And how do you move from where we're at today with a high reliance of Earth to being able to live off the land, or actually live off the resources you get along the way? NASA, like any government organization, actually writes strategic plans that maybe some people read, but most don't. And in our strategic plan that was published in 2014, the first time ever in writing, it said we're sending humans to Mars. That had never been in any NASA strategic plan officially until 2014. Another interesting piece of data. I found that intriguing to myself. And the way they actually wrote the statement up here is, again, that extending human presence further and further away from Earth. Of course, Mars is along that path line for us. In addition to that, the other statement here is about the science side of it. We're going to do a lot of this for scientific reasons as well, and this is a corresponding science piece that's in the strategic plan as well. But lacking kind of, if you don't lay down, like, go to a certain place by a certain time, then how do you start making decisions on what's important? And how do you prioritize what you're doing? To do that, we actually started internally and externally developing a set of what we call guiding principles, things that we thought were important to us in order to make decisions with. And we've laid out 7 of them right now. The first one is related to budget. Living in the near term with our resources that were given through the Congress and congressional appropriations process, without any illusions that we're going to get some magic super billions of dollars in the future. And so let's not architect a human spaceflight program that then requires multiple tens of billions of dollars extra from the US government, but rather let's actually build an architecture that is sustainable with the current budget levels that we have for NASA. And see if we can build have the space economy actually start helping contribute to these things as well. Next one is science enabling exploration, exploration and enabling science. This is actually a line from our old ex-chief exploration scientist who passed away a couple of years ago. He liked to say this all the time. At NASA, there was always these kind of 2 stovepipes. There was a science side and there was a human spaceflight side. And thou shalt not talk between the two, which isn't very productive, just for reference. Because they're sending out Mars probes, they're sending out even heliophysics. You're going out and measuring the sun's activity. Well, maybe you put a radiation sensor on there that monitors the entire radiation environment in our solar system, and then we can then build that into our human spaceflight models and all that. Those kind of dialogues didn't occur years ago. They are occurring now. Next one is related to technology portfolio. People always like, is technology ready to be used? Is it reliable enough to be used now versus later? So this one just really speaks to, let's always have a balanced portfolio of the things that we need in the future, and also then use the high technology readiness stuff here in the near term. The next one is mission cadence. So in previous NASA incarnations of human spaceflight architectures, there was a program called Constellation. And those that are space kind of followers knew about that. Constellation had long periods of time that had no flights going on. Neither robotic nor human missions, and they had these large gap periods of time. We're in one of those right now with the shuttle to SLS transition that we have here, that if we would have planned differently, we could have avoided as well. But how do we actually set up an architecture that doesn't have long periods of time where we're not flying humans in space and or even executing robotic missions on a regular basis? So how do you get a mission cadence? So let's not try to do the gold-plated solution that absolutely will work, but let's do a smaller sequential set of missions that we can roll out faster. That may not sound all that earth-shattering, but that was not the nomenclature in a lot of our planning at NASA several years ago. The next piece is commercial business. There's obviously a very growing and large and increasingly growing space commercial business out there, and how do we leverage that in what we're doing, not just for commercial cargo and crew, but Earth observation and using Earth observation type technologies and companies to then do maybe observation of Mars or the Earth, and how do we start applying some of those commercial capabilities into our overall strategy we have. The next one is multi-use evolvable space infrastructure. So let's try to minimize the number of unique new elements that we have to design and then physically reuse them as well. For Apollo missions, pretty much everything was thrown away every single time you executed a mission. It's really good at building reefs, but it's not very good at building a space program when you have to throw everything away. So how do we get into multi-use of that? And in fact, there's even Saturn upper stages now that are in these long orbits between here and the sun that we find them ever so often as they come whipping back around on their disposal orbit as well. So how do we get about reusing it? Station today, we have been operating over 15 years. By the time station's done, those modules for habitation will be in 30, 40-year modules. So we can build habitats today that last 30 or 40 years as a structure. You need to put the life support systems in it and such, but you don't need to refresh the structure every time. So why can't we use the same structure to go to Mars multiple times, like in a cycler kind of arrangement? Last one is international and commercial. We're not going to do this by ourselves. With just NASA by ourselves. And along those lines, we've been working on an effort called the Global Exploration Roadmap. And we have 14 countries now that we're working with, all the major spacefaring countries around the world. And we actually came up with a common set of goals and objectives and documented it for the first time, which is an interesting process in itself to get 14 countries that have very diverse backgrounds and objectives in space to actually agree. And we have done that as of a couple of years ago, and we're actually doing an update for it right now. In addition to that, there's a lot of knowledge gaps about where we want to go. I mean, about the places we want to go, whether it's the moon or asteroids or Mars. There's certain things we just don't know about the environment. We actually wrote those up in a set of strategic knowledge gaps. We initially did a set at NASA. We have assessment groups, which are kind of us in academia and even commercial folks for the moon and small bodies, which is asteroids and Mars. And they added more content to it, and then they actually vetted them worldwide with the scientific communities, again, through that 14-country process. And we have a common set of strategic knowledge gaps, or understanding of science measurements for all of our potential destinations on our near term, being Moon, asteroid, or Mars. And those are actually all publicly online and published, and not actually controlled by NASA, but rather the assessment groups that are their external organizations. They found interesting things that aren't all that surprising: radiation, regolith, understanding the properties of the regolith that are there, and reliability of systems. As we dug into reliability measurements and such, we find other interesting traits there that I can talk about. Volatiles are the use of the material either from air or, more likely, the regolith, and actually separate out water. Years ago, when we did our initial human architecture plans, we hadn't found water on Mars yet. Nor have we found the water that's on the moon that we now pretty clearly understand is actually there. So we didn't make some of those assumptions, but all those are kind of looking at the commonalities across all the destinations. The other side is instead of NASA just writing a set of requirements in the past and then going building a piece of hardware that they think is needed, we've actually approached working with industry in a totally different way, which is in our world, we have certain ways we can engage the private sector in a fair and open competition way. And we've been putting out things like what we call requests for information, or broad agency announcements, or BAAs, what we call them. We have our legal mechanisms that we do have to work with, but try to seek input through multiple areas of how industry sees the future, not just how NASA sees the future. So we've done that in very visible ways, like commercial cargo and commercial crew. And now all U.S. cargo is going up on our commercial cargo flights with SpaceX and Orbital, and we'll actually be following on that under competition right now with the next cargo contracts we have. We just awarded our crew capability to SpaceX and Boeing, and they'll be flying within the next 2 years and starting to do crew rotations in addition to the Soyuz that we use today with Russia. And that was, we did that over. Everybody thinks that we did that overnight. That was far from the truth. And it took us 7 to 10 years to get there with us in industry. Even SpaceX took 7 years from initial design to first flight of their capability they have today. So it wasn't an overnight thing that occurred. Rockets are still hard regardless of who builds them. But we worked with industry on how to design that acquisition approach and how NASA works with it in a very interactive way. In addition to that, we've been talking about this asteroid mission that's out there. So we actually did a series of interactions with the commercial industry there on things like solar electric propulsion. So Industry's really interested in solar electric propulsion for like upper stages to move communication satellites and such around. So how do we size what we need for a large mission like our asteroid that is also compatible with what they need for their industry use? So we explored that through a BAA. We ran another competition called Lunar Catalyst, where we actually said, okay, we've built a bunch of in-house expertise on landers. How do we share that with industry in order to accelerate their ability to land on the moon? And we actually selected 3 companies, and I'll talk about those as well. Even things like Mars Telecom RFI. We actually put out a thing to the telecommunications industry and said, how should we buy telecom services for Mars from you? And they suggested some outcomes there. And then most recently, we did a next step BA, which is looking at habitation and some additional deep space CubeSats and some even more advanced propulsion systems that industry may be willing to look at. So people talk about, oh, well, like, how are we going to get from here to Mars then? Well, the answer is we don't know, and that's okay. We know the near-term decisions we need to do, and we know kind of how all that feeds together all the way to Mars. But if we were to lay out an exact path from here to 25 years from now, we will be wrong, first off. You can't predict technology that far in advance, I'd argue. And nor can you take advantage of all the changes that will occur over that period of time. So we started an effort called Evolvable Mars Campaign, and all it is a series of trade analysis. So we've been going back and revisiting our design reference missions from Mars and all that, and finding all the problems with it, and then reanalyzing those trades. So how do we didn't understand there was water on Mars and the moon. So now how does the effect of water on Mars and moon change our entire philosophy? So you don't have to launch everything from Earth to take you to Mars, but rather you can at least make your propellants actually for your return trip from Mars on the surface of Mars. That's very feasible at this point. But maybe even lunar resources could be your outbound fuel to get you there in the first place. So we've been looking at that. Other Mars concepts originally were big, large, monolithic habitats that we put big engines on, and we send them all the way out, and then we bring them all the way back. But what happens if we modularize that and split up the habitation? There's other challenges, like complex things like hyperbolic rendezvous and those kind of things, but maybe we can actually think about different architectures. So we've been reanalyzing all that work as well. I'll skip over this. So some of the things we looked at are, could the moons of Mars actually be a good stopping point for us? Could they, and so we've been looking at the Mars moons, Phobos and Deimos, quite a bit in the past year. They have abundance of resources, water, potentially in the 20% range or more on Phobos. If you actually are in orbit around Mars and you didn't want to go to the surface right away and you wanted to snuggle up with Phobos, it would actually block 30 to 60% of the radiation while you're in orbit, because you got Phobos on one side and Mars is 60% of your sky in the other. It's a nice radiation shielding effect. So we've been looking at that. Transportation analysis, redoing a lot of our trajectory analysis and looking at optimization for that. Staging, where do we build all this stuff? You don't just launch it all as one ship. You have to actually assemble it all in space, and where is the best point to do that? So we've been looking at all this and even like co-manifesting of cargo on the large launch vehicle. On the trajectory piece, or a place to do assembly, this is an interesting chart that I don't know if it'll come over in the graphic here as much, but online you'll see it. Basically, it's a graphical depiction of how much energy it takes to go, or the gravity well, basically, effect is probably an easier way to say it. So Earth here is obviously at the deepest point, surface of Earth. The moon has its own gravitational point here. Lagrange points on either side are actually relatively neutral. That's why they're Lagrange points. And so you can see how much energy it takes to stay at any given location. ISS is here. Geosynchronous satellites are here. That's why GEO stay there with almost no energy at all. And what we've been looking at is staging points, what we call a lunar distant retrograde orbit, which is basically this intersection point around the moon. It's about 75,000 kilometers or so. That basically takes almost no energy to stay at. And you're fundamentally stable with no energy input for 80 years once you put something in that orbit. That's an intriguing place to put things and assemble things. It's pretty far out there, but it's within a 3 or 4 day trip home. But you don't need a bunch of energy to keep it there either. So when you hear NASA's talking about parking an asteroid there too, lunar distant retrograde orbit, we wanted to park the asteroid there so it didn't go anywhere. And even if it went anywhere, it wasn't that big of a deal. Actually, it's not that big of an asteroid. The size asteroid we're dragging back, those size asteroids actually come by Earth pretty regularly. And a couple of them, 2 to 3 per year, actually hit us. and they burn up 100%. But this is a really stable orbit location where we can park and assemble large structures. And more importantly, it's a place that we can actually park things when we bring them back and reuse them as well. There's a bunch of things we want to be able to advance, all the different capabilities. Habitation, we want to actually spend some time actually getting the reliability and life support systems and all those kinds of things ready. We are building the new SLS rocket, an Orion capsule, but we need a lot of other systems, and we need a way to get those up there. So one of the pieces of our analysis shows that we need to be able to co-manifest cargo. So whenever we're building the new upper stage of the SLS here, we wanted to be able to fly more than just Orion. So how do we make sure we can fit Orion, but then also launch cargo? So we've been analyzing different co-manifested options. You could take the big rocket SLS and put an outer planet mission on it. People were looking at Europa and those kind of things, and you could get out to Europa and cut multiple years off your mission duration. Or you could launch Orion with an initial habitation system. That would extend its days. Right now, Orion's built for 4 people for 21 days in deep space. This kind of module added onto it, now we're at 30 to 60 days in deep space. And if you build this like the right Lego pieces, you can snap them together and actually build up something that would be on 300-day plus durations over a period of time. You could also, this is ARB, sorry for the acronyms, but Asteroid Retrieval Bus. It's an electric propulsion system, a very large one. It carries 14 tons of xenon in it. And this kind of propulsion bus could get you back and forth or back to Mars in 2 to 3 years, which is great for cargo, but not that great for humans. And then if you don't fly Orion with it, then you could start looking at multiple habitation and lander situations, or the next generation telescopes that are 4 or 5 times the size of what Hubble was. And then even very, very large habitation systems and inflatable structures that would be basically almost the equivalent volume of the entire space station, but launched in one launch, to give you a perspective of how big that is. And that would fit on there. So what does this kind of look like from a Mars architecture point of view of how things go to Mars? So what we're figuring out how to do staging. All of our destination systems, we are looking at actually pre and placing them robotically ahead of time. Send them out kind of on the slow boat through electric propulsion, whether it's Mars moons or the surface or an orbit. You pre and place that so you know that your destination systems are working before you send folks. You use this distant retrograde orbit to do your assembly of your transit hab that you want to send back and forth to Mars. You assemble it in a distant retrograde orbit so you don't have to use a lot of propulsion to keep it there. At some point, the crew that's actually going to go all the way to Mars then also rendezvous with it, either in that distant retrograde orbit, or there's some advantages potentially of taking it out of that orbit and actually meeting up in what they call a high elliptical orbit around Earth. And we meet up and then we're on our way to go to Mars. But again, just keeping it as the place to stay. Then the crew would actually transit in less than 6 to 9 months. And we're even looking at hybrid structures or hybrid engines and stuff. Right now, that's with a traditional chemical engine. We also have investments in nuclear thermal propulsion as well that could shorten that down. And the latest kind of thought is actually combining high power solar electric propulsion with a chemical stage. And you're actually using electric and chemical at the same time. And that is actually a very efficient combination that would get you closer to that 6-month duration getting you out to Mars. The most important part in my mind, though, is on the way back, you don't throw any of it away. The entire stack coming back from Mars gets parked right back in orbit at the Lunar Distant Retrograde Orbit. And the only thing that comes back is whatever crew capsule it is. And the crew could actually, at some point, jump off and come all the way back to Earth. Again, it has to be within that 21 days, because that's all they have in the capsule itself. Or you can actually bring the whole thing back, and then Orion can shuttle between Earth and the Moon. And then you have a habitation system there. You do an outfitting of cargo, maybe even commercial cargo out there, and it's ready for its next trip or its next round trip out to Mars. So it gets along that cycler kind of concept, but not quite. If you looked at Aldrin cyclers and some other things that are out there, there's a value of being able to keep it in place to do the retrofit after. As such. So there's a lot of different technologies that we need to advance, and that's what this chart's talking about, from landing large masses on the surface to the large-scale solar electric propulsion. We still need surface power. Surface power is, at this point, is looking like we're going to need nuclear surface power, nuclear surface reactors. Solar is 3 times the mass to land on Mars as for nuclear for the equivalent power production, if you look at the total system mass. And Mars is a pesky, dusty place where you drop 0.2% per day of solar array efficiency just from the dust settling. So you have to have some kind of active system to clean it off. Now there's techniques potentially to do that with electrostatic discharge and some other things that could be intriguing as well. But right now we're looking at nuclear surface power. And then kind of generating all of our in-situ resource, generating our propellants and even consumable water and such on the surface of Mars itself. So that's a little bit on the architecture side. And now what I was going to dive in and give you kind of a view of some of our actual real investments in hardware we're building. We split things into kind of 4 categories: habitation, vehicle systems, these are your landers and in-space propulsion, the crew itself, think space suits for the most part there, and robotic precursors or probes that we want to send out there before we actually send the humans. My group, this is a bunch of text here that explains what these areas are. But we're a group of just shy of 600 people across the country, including here at NASA Ames down the street. We manage everything loosely in the project form, although I hate the word project even, because that invokes too much bureaucracy and structure in the NASA community. These are technology and capability development efforts. We measure everybody's progress by technical milestones only. So their only product and only deliverable to me is whatever they agreed to demonstrate in the time that they agreed to demonstrate it. All the other paperwork is ancillary, in my opinion. So we have 72 milestones, and actually my goal is actually just to have 80% completion on them per year. So we have a high rate of, in NASA world, we have a high rate of failure of reaching milestones as well. And a lot of it's actually in flight. So we are designing the next generation spacesuits. So what you're looking at here is the backpack, the portable life support system. We have an engineering unit completely working, first one in 30 years. The spacesuit backpack that you see on the space station today is about 30-some-year-old technology with minor upgrades since it was originally built. That backpack is now in human testing, human-in-the-loop testing as we speak. We're doing the next generation spacesuits as well that are significantly lighter weight. We're on our 2nd design iteration of those. And then we're even testing kind of one-off designs of extremely lightweight spacesuits by taking our ascent-descent suits. If you ever saw the shuttle Pumpkin suits, the orange suits, taking the same modular portable life support system, putting it on the back of an ascent-descent suit, and you can do a short duration EVA with it. So it's very modular in design and on different garments and different backpacks. A bunch of other investments. We're the ones funding the work with Bigelow for inflatable module demo on the space station. So this is interesting, and I have a graphic of that I'll show you in a minute. All the next generation life support system, whether it's water recovery, atmospheric, remediation and environmental monitoring, to things like radiation protection. We build all the radiation sensors now for all the vehicles. We organize that into one common group, so we have a commonality of radiation sensors across our entire portfolio. And every flight that we fly, whether it be robotic or human, is flying a radiation sensor now. And we're getting that kind of data, including the Mars Curiosity data on transit. And now we're operating every day on the surface of Mars today, to things like our 3D printer that we did with a local company here, Made in Space, and actually printing ABS plastics on board station today. And later this year, we'll fly up an actual unit that fits in one of our lockers on board the space station that's more of an additive manufacturing facility that will be permanently up there. This was more of a test. To things like large-scale fire. Fire is bad in space. It's kind of bad everywhere. But in space, we don't really understand large-scale flame effects. The largest thing we ever burned in space is the size of a Post-it note, 4 inches by 4 inches. This is going to be a meter by half meter. Really big flames? Maybe. We don't actually know. And we're taking it to the space station in one of our commercial cargo vehicles, orbitals. And after, the key thing is after we undock, when it's done, the last thing the astronauts do is they pull our safety pins for all of our pyros. And after we get away from station, then we'll actually activate our experiment and cause the fire to occur on the inside of the module. And film the whole thing in high definition TV and see what it actually does. We have theories about large scale flame dynamics and all this stuff, but we've actually never done it. And where this matters is because we don't understand it, we don't really understand how to pick the better materials, how to do design. So what we do now is we test the hell out of everything, which costs a lot of money. It'd be better to have some physics to base our models off of than just physics by themselves. Sometimes things don't behave the way we model. So look for that. That's actually coming up late this year, well, actually early next year at this point. So getting back to the Bigelow module. So we initiated discussions with Bigelow 2 or 3 years ago at this point. They've, over 10 years ago at this point, they actually licensed exclusively the TransHab technology for those that are kind of space followers of things. And they've been advancing the inflatable technology on their own and in fact flew 2 modules themselves. We said, that's great. We'd like to actually fundamentally understand how inflatables work in orbit because we never human qualified them or qualified them to put humans inside of them. And even their Genesis modules weren't fully instrumented in order to really understand all the effects that are occurring. So we entered into a contract with them, it was actually cost sharing kind of arrangement with them where we're going to fly a module up to the space station. It's about 16 cubic meters in volume, which is fairly large. And it's going to be fully outfitted with radiation sensors, thermal sensors, and everything else. There is no active environmental life support system in it, so it's completely passive, and it actually still holds temperature, even in space, because the wall thickness is 18 to 24 inches thick after it's fully inflated and all the kind of offsets and everything else. So it passively holds temperature at a comfortable San Francisco temperature, basically. It's today, about 66 degrees or so is the lowest it'll get on its own. And it'll be in the high 70s at the peak sun angles we have. To orient yourself, this is the cupola, big picture window. This is node 3. That's node 3 aft, the port that it'll be in. So it'll be really kind of neat to see that. Brought a video. This has been out there for a little bit, but it will come up on a SpaceX Dragon. People ask, well, how did you decide how big to make it? It was the biggest size that would still fit in the trunk of the Dragon. That was the design requirement. So we have 6 inches of clearance, I think, is our tightest clearance on the one side. So a robotic arm will take it out of the trunk. It'll bring it up and berth it onto the port. I'm trying to convince the station folks to leave the windows open because that would be a really cool video of that moving around. They probably won't agree to that. But and then actually, before the inflation actually occurs, as soon as it's docked onto the station, the crew goes in and actually does a little bit of outfitting and plugging in cords, then closes a hatch. We actually have a reverse pressure hatch, which normally you want to keep pressure from coming in. We actually want the Bigelow module not to push pressure into the station, so kind of in a reverse. So they put all that in place, and it actually inflates on orbit up to this station pressures we have. And then we'll get tons of data on how it performs with radiation and thermal performance. One of the big speculations out there is metallic structures, when you have radiation energy hit them, they basically have a secondary event, and that one high energy particle splits into multiple lower energy particles. And the biggest problem with radiation is actually particle to cell interaction. So if you have a single particle going through you minimize the number of cells, you have more particles going through, you have more cell interaction. So the theory is, with a soft-sided structure, you don't create the secondary events. We don't know. We've actually never flown a soft-sided structure like this in space. And then the thermal control as well. And then for this, there's tons of benefit for us using these modules for exploration, and benefits for Bigelow as they endeavor to build a commercial space station out of these type modules as well. Vehicle systems. We've been testing advanced guidance, navigation, control for landers on our Morpheus and All-Hat test bed. We just finished up flying earlier or late last year. Looking at modular power systems, we've been not so much building batteries and all that kind of stuff ourselves, but actually packaging batteries and fuel cells and that kind of work as well. I talked about Catalyst helping accelerate some of our commercial companies. And we do other things like fiber optic sensing systems, and even back in the NERVA days in the 60s, they had nuclear rockets they were building. They had the really bad idea that nuclear rockets were going to take off from the ground and fly all the way up. That's probably not the brightest idea now that we understand the radiation effects of that. But for in-space propulsion, after you've already left Earth, nuclear thermal propulsion is still a very efficient propulsion mechanism. And we're right now trying to recover the ability to actually make the fuel elements that they built in the 60s in order for us to potentially use them on future in-space stages. as well. So Morpheus, we very spectacularly 2 years ago, August in 2013, had our first test vehicle. We took it down to Kennedy. We were really confident. We had done a bunch of tether tests. We were on our second flight coming off the pad at Kennedy, went up about 3 meters, and then careened over and slammed into the ground and exploded on live television into a big fireball. I was watching it live. This is my first day back from vacation. And it was, it hit the ground, you hear the initial explosion, and everybody's, ooh, I'm like, wait for it, because the tanks hadn't ruptured at that point. And I go, that probably about a minute and a half. About a minute and a half, everything basically hit the peak pressures from the flames, and we blew all the tanks at once and caused a nice big fireball. My only negative about it is it was live on CNN and everything else that evening, but they used the low-def video. We actually had 3D HD. I don't know why, but it was like this horrible video of it. But in seriousness, though, it was interesting that NASA has this failure is not an option kind of culture. And how the agency and NASA reacted and the public at large reacted to a pretty visible failure. It didn't hurt that in the same week time frame we landed on Mars with Curiosity, doing something that nobody thought would actually work with a sky crane and everything. And then we wreck our next generation lander within 7 days of that success. And it kind of showed the challenges and successes of the space program all in 1 week. Within 4 hours after the test failure, we committed to rebuilding the vehicle and got back to flying. There's a good lesson here. After 4 flights of the new vehicle, we were already exceeding the performance of the previous vehicle after it had been flying 30 times. So if you look at technology S-curves and how you come up on and reliability of your systems and everything else, failure is really, really good to get you to start over. And it was a good learning experience. And that culminated actually with a night flight, which was really, really great to see the folks there do that. I got a short video here as well, and I'll narrate a little bit for you. Morpheus, to give you an idea of how big it is, it's about 12 foot by 12 foot by 12 foot high, and about 5,000-ish pounds. The engine on there is a liquid oxygen methane engine. It doesn't fly that fast. I sped it up. But in this flight, it's going up 800 meters. That's the shuttle landing facility. That's the vehicle assembly building. It's actually higher than the vehicle assembly building when it's flying right now. That's our advanced optic systems for a laser Doppler ranging system. So it's actually doing an active scan of this hazard field down here. That's a simulated portion of the moon. And what's interesting is, what people don't realize is when it went up, it was given a command to find where it should land on its own. And so it's scanning the hazard field in real time. It's calculating and finding its position of where it should fly. And then it's calculating all the navigation algorithms and everything else in a closed loop design, all in less than 6 seconds on a 92 core processor, all on board, while flying at nearly 90 miles an hour downrange to land as well. So it was a great success in that it's the most accurate landing system we've ever built that could be directly applied to space type projects. When we land on Mars today, we're lucky to have 20-kilometer landing ellipses accuracy. We need to be able to get that down to 100 feet. And that's what we've been driving to do with those kind of systems. We learned a lot about landers and such, and we figured that's what better thing to do than share it with the commercial industry. So we ran a thing called Lunar Catalyst, where we competitively selected 3 US companies that are building lunar landers for their own needs and own benefits and own customers. And we selected Astrobotic, is based out of Pittsburgh. They're one of the Google Lunar X Prize teams. Zeus lander from Maston, they're out of Mojave here. They've been doing a lot of suborbital work and have desires of building systems to get themselves all the way to the moon. Their Zeus concept, this is actually an upper stage of a current rocket that ULA uses. And they actually put these pods on the side of it, so you actually take the entire upper stage and you land it on the surface of the moon. And then Moon Express, who's actually over here at Moffett Field, that's been progressing towards their flights as well. And in fact, they just completed their first series of flight testing down at Kennedy in the same test area that we've been testing at as well. We do a lot of other work in like operations systems and operations management and automation. We have our own kind of core flight software that we use. It's It's our kind of open source internal for government kind of open source release for, that we're actually porting versions of it out there for others to use on things like UAVs. Avionics, we look at different avionics architectures. It's a Raspberry Pi in the picture, but we've figured out how to commingle different avionics systems so you can have a state-of-the-art, say Boeing 777 type of computer in the same voting architecture as a Raspberry Pi, and they intermingle just fine. And to a reliability level that we would want for human spaceflight. So that's an interesting thought process, how to get to voting structures and different avionics. We've been the lion's share of the investment behind disruption-tolerant networking, DTN networking, which is basically an additive layer on TCP/IP to get rid of the latency issues and add basically a bundle protocol stack to it. And then even next generation things like arraying antennas. So we take commodity antennas, several meter antennas, and we actually put them out and we actually broadcast them all together and form a beam, a coherent beam, as all three of the antennas actually transmit together. It sounds really easy, but you have to take into account the entire atmosphere from where you're transmitting from to space, and you have to cancel that all out in real time. So we do that now, full closed loop arraying of satellite dishes. And we've actually arrayed, if those are familiar with our deep space network, we've actually arrayed a couple of our 34 meters with the 70 meter. And so you can think about the amount of power and gain that you get out of those large antennas, 7 meter being one of the largest we have in the world. And we can actually add them all together and throw up a hell of a lot of RF power. And we actually just recently tried to use it to rescue one of the stereo probes that we hadn't heard from. We believe our arraying worked, but the satellite's just not responding at all. So we basically threw up every bit of power we had that we can literally kludge together and tried to punch into the spacecraft in case it was facing the wrong direction and get a strong side lobe RF signal to get into it. The long-term plan for this is space-based radar. So how do you radar asteroids that are way, way, way away to a really high resolution? To even being able to use the radar to interrogate the surface of Mars to figure out no drive zones or where the traction may be different on surfaces of Mars. If you see our Mars Curiosity, we see sand dunes and we didn't expect to see them. With a radar like this, we can actually see all the way there and actually understand the density of the surface and figure out where not to drive. And we can do that from here. The end result here is 50 elements to 100 elements all arraying together. And you can actually have them geographically distributed across the country. And you can actually phase up the entire array at once, which is pretty interesting. DTN, our delay tolerant networking stuff, we've actually been developing a lot of the code through a series of open challenges and software challenges, and been giving out prize money and such to get some of that code written. We've been building a bunch of probes to go out there, everything from Resource Prospector, which is a mission that we're potentially partnering with JAXA or another international organization to actually go prospecting on the moon, to figure out where the resources are identified at. We're building 6U CubeSats and sending them into deep space to understand things like biology, but also a low-cost probe to fly by an asteroid and do measurements there. And CubeSats are kind of in a really interesting emerging area. One of my other jobs is I run our CubeSat launch initiative for NASA. So NASA's been launching CubeSats now for 5 or 6 years, spearheaded by NASA Ames down the road here. But we wanted to be able to accelerate all the university flights. And what we've been doing is opening up access to all the universities and not-for-profits across the country. And we have over 100 and some satellites we're flying in the next couple of years and have flown. From all the states across the country. I'll skip these two. Mars 2020, we got next generation prospecting instruments that we're sending to Mars. Our group's building a lot of those and instrumenting the new back shield to understand the atmosphere as we go into Mars. This is that contract I talked about. I'll leave these for you guys to be able to have online, but wanted to leave some time for questions and such too. But the fundamental message is we are approaching the human spaceflight kind of planning process in a totally different way. We're not going to lay out like stepping stones from here all the way to Mars because they'll be wrong. We actually want to work with industry to build actually more of a space economy along with hitting our exploration goals in concert with that. And sharing as much of the technology advancement we have with industry that wants it as well for their own commercial interests, and we're seeing that growing significantly these days. So I don't know if you guys had time for questions.
Anyone has any questions?
Hey, thanks for the talk.
Yeah.
So I'm curious, we're looking at both commercial exploration and government exploration. What do you think, who do you think the exploration personnel will be in some of these missions? Do you see it ultimately being driven by like commercial employees who are going to those? Or will it be like NASA astronauts but enabled by commercial technology as well?
So it depends on what you mean. So I see there's always a role of exploration and then there's a role of pioneering. So exploration is the purpose of going out and finding something that may or may not be of value. And then the pioneering piece kind of drives the economic piece behind it. For things like commercial crew and all that kind of go to station, NASA's just buying it. And some of the initial astronauts on that may be a mix, actually, crew of commercial and NASA astronauts. If we're sending crew into deep space for the first time, there's not really an economic return for that yet at this point. So if some company can actually forge and plot their own destiny to launch a ship into deep space, more power to them. I mean, we're not going to stop those kind of things either, but we'd actually rather see kind of industry and NASA kind of coming together where there's no economic turn in the near term. I think that's where there's a unique kind of government investment role where we can buy services and actually work with industry. And then as the benefits are better understood, then we as NASA actually just become a customer at best, and maybe even abandon some of those things. Low Earth orbit, our desire is after the space station's life is we would just utilize a facility in low Earth orbit that's probably commercially operated. And we would just be a tenant. We would just use it for whatever experiments we need to do it from and turn over operations and everything to a commercial entity. That's our desire there. I think it's a hard hurdle though on this economic return piece because even as much as costs have lowered, it's still pretty expensive. So I don't know what it will be, but it'll probably be some kind of mixture in the future. But yeah.
Just to go back to kind of optimizing for when you continue to improve on technology versus just building something out. You had mentioned lighter weight spacesuits, and I'm just wondering why that would be a concern with Mars having about a third of the gravity of Earth.
Yeah, so our current spacesuits, even with a third, are in the hundreds of pounds. Oh. So even at a third, you're still carrying 150 to 200 pounds of relative weight after you've traveled 6 months in microgravity. Special Forces troops in top shape carry 150-pound packs, but not after a 6-month trip in microgravity where you may degrade your capability. So we do want them lighter weight. And the other side of it is, if they're lighter weight, we can bring more spares and more spare parts. Because the number of EVAs that we did for a space station, everybody thought that was impossible. And when we get to a planetary surface like Mars, we're talking about multiple EVAs per day. And so we're probably going to need to bring a lot of spares in addition to that. So, yeah.
Hi, I'm Tilek. I have 2 questions. First, you talked a little bit about international collaboration. So I was wondering if you could talk a little bit about the challenges there and maybe also some optimism. One thing I heard, for example, about Russia is that even when there were sanctions, there was still collaboration around space exploration continuing. I was wondering if you could share an update on that and talk in general about collaboration. And second question, if NASA is looking into asteroid mining at all, or what's NASA's position on that?
Yeah, so on the international front, I mean, the history will show, we started cooperating with the Russians during the Cold War. And so we were cooperating with them at a point that we weren't cooperating on anything else. Besides buzzing each other with planes on various borders. So the recent turmoil with us and Russia and Ukraine and all that, the human spaceflight and science kind of community was exempt from it. And cooperation still continued. Even though you hear rhetoric in newspapers and press and all that kind of stuff, it didn't actually impact any of our operations nor any of our actual cooperation at all. It was all just rhetoric in the papers and such. But so I think in certain areas, space exploration being one of them, it kind of raises to a higher level and doesn't get bothered by the more localized politics of things. And I think you'll see that continuing as well. On asteroid mining and such. So asteroid mining, there's actually a couple companies out there commercially that are looking at that. We've actually engaged with both of the companies that have publicly declared that they're going after that. And in fact, we've actually awarded kind of joint studies work with them as part of our asteroid redirect mission to figure out what do they want to do and what do we want to do and how do we enable them to actually open up their business model. We also share a lot of our technology for how do we process materials and those kind of things openly with the private sector as well. We currently don't have any, NASA doesn't have a plan to mine asteroids ourselves, but we're also not going to stand in the way of any commercial companies wanting to do it. And in fact, we want to help enable them if possible.
So the SLS, I was wondering how many launches do you expect it to have per year in order to make it commercially viable? Well, not commercially viable, but at least that worth the price that you're paying. Because it seems to me that when it comes to robotic missions, other launchers seems to be much, much more efficient in terms of how much you pay for them. And even bigger robots, okay, imagining sending like really large space telescope or things like that really cost a lot of money. It's not that you can launch 2 or 3 of them a year. So SLS seems to be mostly geared towards like human exploration, especially for this space, but you don't appear to have an objective there. So I'm really wondering, you know, whether you will get to a point in which you realize that you need an objective in order to be able to justify SLS, or you'll cancel it outright.
Yeah, so every one of our human spaceflight architectures requires a lot of mass in order to send ourselves to Mars. And so the original rationale for a large rocket, whether it be SLS or Ares 5 before that, was basically based on that mass. We still require that large performance. And it's really what we need, that large performance, not at low Earth orbit. So you hear SLS being talked about at 107 metric tons or 120 or 130 metric tons. That's all compared to low Earth orbit, which is actually somewhat irrelevant, because what we need is mass delivered to some place like a DRO, and that's a better measure. So if you look at the co-manifested things I drew up there, that is being able to get us a mass equivalent of 25 to 40 metric tons in a DRO orbit. If you did that with any of the existing ELVs, expendable launch vehicles, or commercial launch vehicles that are out there today, that would still take you 5 to 6 flights per. So we're looking at flying SLS at a rate of about 1 to maybe even 2 per year in the out years, which is not that much. And it's mainly at the point is we can't just launch hundreds of rockets to get to the same mass equivalent. Because it will be, there are certain modules and certain pieces of the architecture that you just can't assemble once you get up there. They say like a main propulsion stage or something like that.
But if you allow me a follow-up question to that, I mean, the first launch of the SLS, you know, to the full capacity that you're claiming at this moment will happen only within, what is it, 10 years perhaps?
So right now we're looking at our first EM1 mission, which will be uncrewed. That will be the initial 105 metric ton variant of it. We'll send Orion up into the distant retrograde orbit and back. The second version of that is where we're looking at doing the upgrade to the upper stage, which will get us not to 120, but not to 130. It's actually kind of in the middle. The current design is around 123 metric tons of performance. Basically, it's everything we need to do besides replacing the solids on the side. That's where you get the extra bit of a performance. So on the second flight of SLS, it will be the flight configuration that we plan on using to deploy all the heavy objects out there. So on that second flight of SLS, we have the option to fly Orion and a habitation module on the second flight,
so
if we wanted to.
When will that become operational?
2021.
So we're thinking about, like, SpaceX, the Falcon Heavy will probably become operational within like 3 years maybe, and it's like a third of that metric ton.
So Falcon Heavy is in the 50 to 60 metric ton to low Earth orbit with no upper stage. Yeah. So you get 60 to 70 metric tons to low Earth orbit. So you're the same equivalent out to the DRO. It'll be 20%-ish of what SLS is. At some point, Elon may keep on upgrading. I hope he does too, because we do need big rockets to send all this stuff. That's why he's building big rockets as well. So at some point, we may see those curves cross, and then we'll change our strategy at that point. That's a fair question.
So I have a question. With the perspective of a Mars mission, are there negative effects of long-term space flights on the human body? And if so, is there a strategy to address that?
Yeah, so we actually track risks. So we have this risk to mitigation kind of approach. And we have a set of group that looks after this called Human Research Group. They identified 28 major system risks, the human as a system. And they come up with mitigation strategies for all those. And they could be anything from bone loss to muscle loss and those kind of things. And for the most part, we're able to mitigate nearly all of them. Bone loss and muscle loss and all those between mitigation regimes on orbit, be it nutritional ones or exercise routines and such. Radiation is another one that's out there. We have a current radiation limit is 3% lifetime increase of cancer for a crew member, so they're like a radiation worker. 3% lifetime increase though. Our current Curiosity model on the transit when Curiosity went out would have increased somebody's lifetime expectancy of cancer to 5%. You can make your judgment on whether that's ethical or not versus the 7 million pound rocket that you're being strapped to. So.
We have time for one more
So
question.
I think there will be a lot of mitigation strategies for that. And then even and I'm not a health science person at all, there's tons of money going into cancer research and such, which has a lot of the same effects what radiation causes. And I think the billions of dollars that the medical industry and NIH and all them are doing will probably start mitigating some of these effects that space travel has on you faster than a NASA investment in it. But that's just my speculation. So.
One more question.
His question was about sort of like the long-term risks. I'm curious about medical care. So right now I know like the most advanced medical technology on the ISS is like an ultrasound, and if someone needs to, has a serious problem, they can get evac within a day or so, right? So I'm curious on the plan for like 6 to 9 month missions. What are the efforts right now going on to be able to provide medical care like at point of care?
Yeah, so we are looking at other miniaturized pieces of equipment besides the ultrasound, things like an MRI and some other things that have on orbit as well. And being able to do limited procedures, actual surgical type procedures on orbit as well. So they are looking at that. Obviously, station itself, if you have a medical emergency on station, less than 17 hours, you can be in a U.S. hospital from the space station. And so that's not a big risk. And this is why actually moving from station to kind of cislunar space, that then goes from 17 hours to 3 to 5 days, maybe up to 9 days of duration before you get home. When you're going to Mars, you're going to Mars. You don't come home early. So if you had a medical emergency halfway there, your abort scenario is to the surface of Mars. You're still going to Mars. So as we will continue, and we actually kind of have like medical device watches and those kind of things where we actually are working with many commercial vendors as they're increasing their own medical technology, actually adopting those and then basically using them in space. And so we're doing a lot more commercial items, including like the ultrasound is not something we built, we bought it commercially. We're actually looking at similar things for MRI and a lot of those. And we're actually even looking at advanced telemedicine type work. And we're really relying on the medical industry to keep on advancing and at the same pace we are and utilize that. It is something we think about, and we have a whole group that's just looking at basically exploration medicine and mitigation techniques. And another aspect of it is screening as well. Screening the astronauts and crew members to minimize the chance of something occurring. If you ever look at a lot of the medical data from astronauts and stuff is actually being made public at some point here, anonymized and being made public. And you see the selection is working because most of them live a lot longer than the average person. And so they are selecting for certain things. But yeah.
Thank you very much for your
time. Yeah, thanks.